happy to have we're extremely happy to have Hanyu Zhu, who's our local. I've never actually invited a single person from local to give a talk, so he's the first person I've invited locally to give a talk. Yeah, so he's a junior faculty in material science and nano engineering. So the reason I want him to give a talk was because mostly I thought, chiral phonon is a quite novel thing, sort of a new, and maybe there's some things that one can learn from a scattering perspective. So Hanyu, it's all yours. Yeah, thank you.
Thanks very much, Fengcheng, for inviting me to this very prestigious seminar. It's my great pleasure to share with you about chiral phonons. I'm an experimentalist, mostly on optical spectroscopy. So I have to make that clear that this concept of chiral phonon is not coming from me. So it's actually a lot of theoretical work has been done. And also Jeff and other people have done many works on chiral phonons with other methods. But today, I will just try my best to start from the very fundamental concept about the chiral phonons, and also including what's the experimental ways to find them. So mostly the actual data that I'm going to show is from my old work back in Berkeley, when I was a postdoc under Dr. Xiang Zhang, who currently moved to University of Hong Kong as the vice chancellor. And also a lot of collaborators of me are going everywhere around for faculty positions. So we also get collaboration in terms of sample and theoretical support from KAUST and also the Nanjing Normal University. So the data was supported by Department of Energy back at Berkeley, but my current lab, which also focused on chiral phonon works and spectroscopy, is supported by the National Science Foundation. So I would like to first review very generally what exactly do we mean by chiral in condensed matter, and then specifically move to a system where chiral phonons can be found in two-dimensional lattices, and then we use optical spectroscopy to detect chiral phonon interaction. So this is very important because we want to actually know what is the effect of chirality of phonons instead of just looking at phonons, which are historically has been done by many people. And finally, what's the application, or what's the relevance of chiral phonons, especially when we can manipulate them coherently. So I think I have 4 or 5 minutes and some extra time for Q&A, right? So I will try to control my time. So
yeah, that's okay. My time is not a huge limit. Yeah, here.
Okay.
Go ahead.
All right. Thanks. So there are actually many ways of defining chiral entity. So mostly people hear about things being chiral in chemistry and biology, where the molecules are chiral because they break mirror symmetry. So something that has left-handedness and right-handedness, and cannot overlap with each other with its own mirror symmetry. So in physics, the chirality is a bit more abstractly defined, especially in high energy physics, where they define chirality with its representation in terms of a four-dimensional space rotation. Well, generally speaking. So that being said, this particle still the idea of chirality obeys the similar concept that if a particle under certain transformation is not identical to itself, then we can say this object is chiral. So because it's defined by this Poincaré group, which includes basically four-dimensional space rotation, then roughly speaking, the concept of chirality means that the object must not have either parity or time reversal symmetry. So we would like to consider a simpler cases. Just let's not take a look at that 4 dimension in total, but reduce the dimension to 3. So there are 2 possibilities with 3 dimension. All 3 dimensions can be in space, so that's a case of chiral molecules. But the chirality of molecules is actually not a well-defined quantity. You cannot mathematically define it. So you can say this molecule is chiral, but we cannot absolutely say that something is left chiral or positive chiral versus negative chiral. So this can be clearly seen by transforming a molecule continuously. So suppose if I have a molecule and then have 4 bonds that are all different, and this molecule is apparently chiral because it doesn't have mirror symmetry, then I can manipulate these bonds. Oh, actually, I think I should switch my pointer. Okay, so that you can see where I'm pointing at. So I can manipulate all these bonds such that this molecule always break mirror symmetry. So it keeps being chiral, but then by rotating these bonds, it is possible to transform one molecule to its mirror image. And this molecule is being chiral all the time. So it is impossible to define left and right because there must be a boundary somewhere in the beginning. Along the path, if there is a absolute left or right. So chiral molecule in 3 dimension is actually not very well defined. Whereas chirality in 2+1 dimension can be assigned some topological invariance. In this case, let's consider a particle that is doing rotation in plane. So for sure, this molecule itself cannot be flipped out of plane. So that's the assumption, and the trajectory of motion of this particle cannot flip out of plane. In that case, in order for this rotation to be reversed to opposite direction at certain point, then the velocity of the particle must pass a point that it is its own mirror symmetry. So therefore, a continuous transformation must remove chirality at some point. So if this happens to be, there happens to be an energy barrier there, then we can say that the chirality of this 2+1 dimension is somewhat protected. So talking about chirality, most of the physics has been focused on fermions. And this is a very simple reason for that, because with fermions, we can talk about ground state, and then the ground state can already break some symmetry already. So let's take a look at the 2 cases where the base lattice of the whole system breaks either parities or time reversal symmetry. So with lattice that breaks inversion symmetry, then there are electronic states called wire nodes in Waals semimetals, where basically the energy dispersion happens to have an accidental touch in the K space. So there's only one energy point where 2 bands touch with each other, and then because the material has inversion asymmetric, then you can prove that the such touching point must occur in pairs. So as long as these two pairs do not merge at the high symmetry points, they're always pairs. And then it's possible to prove that with spin orbital coupling, these pairs actually have chirality, because their spin will be locked with its momentum near the accidental touching point of a well nodes. So this has been well known for some time, and the topological properties of the Waals metals has attracted a lot of interest recently. The other system is probably have a longer history where the chiral edge states of a quantum Hall system since its discovery 34 years ago. Then we know that this magnetic field can break time reversal symmetry and causes this unidirectionally rotating chiral edge states that's coming from the Landau levels. So, and this is actually when people consider the most intuitive idea of being chiral is that just something doing rotation, right? And this rotation must break time reversal symmetry. So, of course, not all lattices break pure T symmetry, but it is also possible to identify a subsystem within the lattice that within the subsystem, the P or T symmetry is effectively broken. So these are the cases where a subsystem breaks the inversion symmetry. It's a case of graphene. So we know that graphene holds Dirac cones. Some people say graphene, the Dirac particles are chiral, but just consider that graphene doesn't break any symmetry by itself, right? So it has two carbon atoms, it has inversion symmetry, it has time reversal symmetry. Then how is it possible that the particles within graphene can be chiral? So the definition actually comes from people just artificially divide its carbons into A and B lattices. And then they say electrons on A lattice will be pseudo spin up, and on B lattices pseudo spin down. So within the A and B sublattice systems, it is possible to define chirality where in momentum space the Dirac cone occurs at the Kn minus K or K prime points, and then each K point actually corresponds to one of the sublattice system, and then the pseudo spin of these Dirac cones are actually locked with its momentum. A similar case can be found for time reversal symmetry. This is the case of quantum spin Hall system, where again these or alternatively called topological insulators, they are not time reversal symmetry broken, but because of spin orbital coupling, and if the spin, so this is a quasi two-dimensional system, and if the spin do not mix each other, then within each spin subsystem, then effectively there is a magnetic field there for each subsystem, and then they still can exhibit a chiral edge state for each of the spin, although their motion must be opposite with each other, such that the overall material doesn't break time reversal symmetry. So these are chiral fermions that people are familiar with. Then we asked the fundamental question if bosonic elementary excitations in solid states can also be chiral. Similarly, it does. If we are looking for something supported by a is something chiral supported by a solid state system. We're looking into bosonic modes that are non-degenerate. That is, if you reverse the chirality, this particle looks different from itself. So under this condition, the lattice must break either, again, P or T symmetry. Nevertheless, because bosonic excitations are always in excited state, so we're not looking at ground state anymore. So it is just possible to inject some bosons that by itself it breaks time reversal symmetry. So the system does not break time reversal symmetry, but we can inject particles that causes symmetry breaking. That also leads to interesting physics, which we'll discuss later. So, let's take a look at materials that does break time reversal symmetry. So, and causes chiral bosons. So one example is the magnons. So this is a very simple example of magnons in antiferromagnetic material, and then it's been well known 70 years ago that they exhibit antiferromagnetic resonance. That is, inside the system, we have two spin sublattices. The spin are opposite to each other such that they cancel each other. So that's why it's antiferromagnetic. But then when the magnetic field is applied to this spin system, they can start to proceed. And then there are two magnon modes that are originally degenerate when there is no magnetic field. But then after applying magnetic field, the magnons split into left-handed and right-handed modes, and they have different energy. So similar things happens to phonons as well. It has been known also for a long time. When people launch elastic waves, so these are ultrasounds in solids, and then when the sound propagates in a material that is under magnetic field, it was found that these ultrasounds, which are shear modes that whose displacement varies as a function of time, so they're rotating when they're propagating like this. And then they, in metals, the ultrasound attenuation is different for left and right circularly polarized ultrasound under magnetic field. So sometimes it's, this in optics, a similar phenomenon is called circular dichroism, but in the field many years ago, it was more called the morphic effect. So then we turn into a different system where, so we talked about how time reversal symmetry can cause bosons to be chiral. Then let's take a look at how inversion symmetry breaking can cause the bosons, in this case, it's a lattice vibration of phonons, to be chiral. So just fundamentally, this is a very general phenomena where as long as you have a lattice that breaks inversion symmetry, and usually the phonon will not be its own mirror image. So it has certain chirality. But sometimes people kind of ignore this effect because, you know, most people don't really care about how the lattice displacement looks like, right? They only care about, well, what is the phonon dispersion, what is the transport properties. But let's use a very special case to see that actually the rotation or the displacement of the atom itself matters for all these properties. But I would still say this, even if this is a special case, the chiral phonon is very, very general in any asymmetric material. So here, we have a hexagonal lattice, and then we have AB sites. Now, we want to say that this AB site is no longer the same, they're actually different atoms. And then we look at the specific mode, so-called K or minus K mode, where the plane wave actually propagates along these atomic lines. Okay, so these are the phase of this plane wave. And then this mode happens to be rotating, say, this B sublattice, and the A sublattice keeps skew. So it is provable that this atom, when the plane wave is propagating to the right direction, must rotate clockwise. And because the system is time reversal symmetric, there's another mode where the plane wave propagates to the left, and then the atoms rotate counterclockwise. So these modes are always coexist, and then they always have the same energy. But how can we be intuitively understand like why this atom must rotate only in one direction? What happens if I just force this atom to rotate the other direction without changing its momentum? So this will be the consequence. So here we launched two plane waves that is all propagating to the right. And then we dictate that in one mode, the atom rotates clockwise, the other atom rotates counterclockwise. Now, look at the force balance. So those are very intuitive, like elastic questions. In the first mode, all three bonds keep the same distance. And then it is possible for the A side lattice to keep skew, whereas in the other mode, because of the phase relationship, those bonds cannot have the same distances. So the A sublattice atom must rotate. Okay, now apparently those two vibrational modes are different, right? So indeed, they not only they have different displacement, but also they have generally have different energy. So in those cases, we can indeed say that the phonon is somehow chiral because you cannot simply change its atomic rotation direction. And this is purely based on the fact that those atoms, there are AB sublattices that breaks inversion symmetry. So the reason we choose hexagonal lattices is because it's a hexagonal two-dimensional lattice. So it's two-dimension, and we're looking at high symmetry point. So the K point itself and the lattices are both threefold symmetric. So they are rotational symmetric, and it's possible to define some angular momentum. So even if phonons are generally chiral, in non-central symmetric material, they usually don't have a good angular momentum. But in this case, we can define something that looks like angular momentum, or pseudo-angular momentum. So the general definition of angular momentum is how the wave function accumulates phase after rotation. So in our case, the Hamiltonian is not continuously rotating. But it has threefold symmetry. So it's fair to rotate by 120 degrees. So then we can follow the same rule. Say if I do rotate this wave function by 120 degrees, what do we expect? How much phase does this phonon vibrational mode accumulate? So not all phonons can be rotated because the lattice itself is only threefold symmetry, and a general point within the Brillouin zone is not threefold symmetry. There are only two places or three places. So in the gamma point, the center of the Brillouin zone, or the corner of the grid is on the k or minus k point. So only phonon on this point can be defined like perfect pseudo-angular momentum or integer pseudo-angular momentum. So the phonon turns out to have pseudo-angular momentum plus or minus 1 because after you rotate the wave function, we accumulate some phase. So let's take a look at this phonon mode. So the three atoms are rotating at different phase, and then now we start to rotate this entire system. Okay. So we rotate it counterclockwise, and then you find that this is nothing but just the same phonon modes evolving by extra phase, right? So actually accumulates minus 2 pi I over 3. That basically means that this phonon modes have angular momentum plus 1. So now we know that the fundamental reason why the phonon being chiral here is that it has some rotational, lattice has some rotational symmetry and its inversion asymmetry. We have already discussed that the features of chiral phonon include irreversible atomic rotation. You cannot reverse the rotation of one atom without changing all the other motions or its energy. But also, we briefly talked about non-degeneracy before, and let's verify how come it is non-degenerate. So because we have AB sublattices, we can prove that on one K point or K prime point, there must be simultaneously two phonon modes, one with pseudo-angular momentum plus 1, the other with pseudo-angular momentum minus 1. This is like basically spin-orbital splitting. Like so you have plus, you must have minus, right? But then the plus angular momentum phonon rotates the B sides, whereas the minus angular momentum phonons rotate the A sides. As long as the A, B sides actually contain different atoms and they have different mass, and then their energy must be different. So those phonons do have energy splitting that looks very similar to electronic spin-orbital coupling. So all this physics looks pretty interesting, right? Even if people don't really frequently discuss the chirality of phonons, but you see these conditions are fairly easily met in a lot of materials. So why don't people see that or measure that in the past? Basic reason is that they generally happens at finite momentum. So in order to break mirror symmetry, these momentum shall not be at the center of the Brillouin zones. At gamma point, there's no net momentum, right? So it obeys mirror symmetry. So we must look at finite momentum, but there are not many tools that can measure excitations of finite momentum. So the scientific question that we would like to ask is, other than being mathematically interesting, if the phonons have chirality, what will be the observable effects? So typically, when people in high energy physics talk about chirality, they are looking at some scattering process that are asymmetric. And then the second goal will be if it's possible to verify that atoms is doing rotation. This is, of course, we do not directly see atoms, right? But by means of selection rules, say polarized photons scattering, polarized neutron scatterings, and compare them with first principle calculations, can visualize how the atom moves. So realizing these two objectives are very different from what people typically do for phonons, where only the energy is the center of research. So, of course, there are ways to study finite momentum phonons that include neutron scattering, X-ray scattering, electron loss spectroscopy, and also optical spectroscopy can also study phonons with finite momentum. That's one example is Raman scattering, where finite phonons with momentum k and minus k are simultaneously scattered. So all these methods measures energy or sometimes even energy dispersion very accurately, but they generally do not reveal this chiral effect. For example, so in Raman scattering, because you simultaneously have phonons with the plus momentum and minus momentum, so all the chirality information cancels out. Even if in these two-dimensional materials, people have known for a long time that a lot of K phonons resonances can be identified. So all these peaks actually correspond to different combinations of momentum of phonons coming from the K point. And also neutron scattering of two-dimensional materials has been there for a very long time. It's interesting that they have never measured polarization scattering, but also even if they do, there won't be effect because bulk two-dimensional materials does not have preserves inversion symmetry, so there won't be any polarized scattering. Then we have to find something that does break inversion symmetry. And that will be very difficult for neutron, at least in this case, because they're going to be single molecular layers. So we're looking at so-called transition metal dichalcogenide, or sometimes people just colloquially call them like 2D materials. These materials have only one molecular layers, usually a few layers of atoms. So they're very simple. They're purely two-dimensional, truly two-dimensional. And all their scattering process are two-dimensional. So these simplifies the physics. And also, it happens that these particular family of transition metal dichalcogenide has some special properties that helps to identify chiral phonons by optical means. So the monolayer breaks inversion symmetry because they are hexagonal and they have AB sublattices. When they're stacked with each other, their AB sublattices basically reverse with each other in alternating layers. So bulk material doesn't have inversion symmetry. That does have inversion symmetry. But monolayer breaks. And then it happens that the monolayers have direct bandgap. So these materials are generally semiconductors, but in bulk, they're all indirect gap semiconductors. So people don't really think that they're of any like particular usefulness. But since about 10 years ago, people discovered that miraculously the single layer has a very strong photoluminescence, indicating that it has a direct gap. So even 2 layers doesn't. So that's a big contrast. And having a direct bandgap makes it very easy to optically detect electrons and holes. Now let's look deeper into the band structure of this material and see how these electronic properties help us to interact with phonons. So other than being direct gap, those gap actually locates at the K point. So this is basically a green light, because both the electron and the hole, once generated, have enough momentum to scatter phonons. So you can study electron-phonon scattering with finite momentum. And then, because these materials are having inversion asymmetry, there are two valleys, so located in different momentum space. So if electrons and holes scatter between one valley to the other, they have the same energy, so they can scatter, but this scatter will be associated with a valley phonons with non-zero momentum, or in our case, it would be chiral phonons. And then this inequivalent k and k prime point, or minus k, gives the electron holes, here is a particularly holes, different wave functions. So you can prove that the electrons have different angle momentum for these two valleys. And then that causes a spin or orbit coupling. So the orbit different, then the spin is also different. So a large spin orbital coupling makes these holes pretty stable in one valley or the other. So basically, because there's a spin orbital splitting, then whenever a hole is generated at the valence band maximum, it will stay there. It's very difficult to scatter this hole from one wave place to the other without changing its spin, because there's just no other states available. So this type of property is pretty unique and generates a lot of interest by itself in these 2D materials, which is called valleytronics. So the idea is once you have optically injected holes, they will stay there and maintains a so-called valley polarization, and presumably indefinitely, as long as the carriers are still alive. So indeed, people got the initial excitement from measurements where the photoluminescence, which is the emission of these carriers after some time, maintains very high degree of circular polarization. So information of polarization is stored within the material. So that's pretty nice. That means we can use this holes or electrons, if they're equally stable, to study some properties that breaks time reversal symmetry. They are spin polarized, valley polarized, and they can interact with chiral phonons. So we talk about chiral phonons in 2D materials. We talk about how the electrons in these materials look like. Now let's finally discuss what's the electron-phonon coupling. So this is the mechanism by which we probe these phonons, because electrons are easier to manipulate than phonons. So we argue that the coupling is also chiral, meaning that you have to have specific polarized phonon to interact with specific polarized electrons. They cannot mix with each other. So this is based on simple symmetry argument with the different conservation laws. First, the momentum must conserve. So that means if you have an electron that scatters from one valley to the other valley, it must emit a phonon that corresponds to the destination valley. And the second is the spin must conserve. So to the first order approximation, we will discuss when this will be invalid later. But to the first order approximation, spin is conserved. So the phonons can only carry electron between the same electron levels with the same spin. The system itself has mirror symmetry, and it happens that both the electron conduction band minimum and valence band maximum has a wave function that is mirror symmetric. So that means that any phonons that scatters those states must also be mirror symmetric. And finally, it comes from the chiral terms, where can be argued by angular momentum conservation. So here it says that the pseudo-angular momentum must be equal to the change of electronic orbital angular momentum plus electronic valley pseudo-angular momentum, because the electrons are in different valley, they look as if they have additional angular momentum. And if there is any external electromagnetic field involved, then the photon itself carries angular momentum as well. So the value pseudo-angular momentum is defined by plus minus 1 for either k or minus k value. And then the orbital angular momentum is defined by the electronic wave function. If it's for dz or dz square orbital for the conduction band, then OM is 0. And if it's a dxy orbital, it's a plus minus 2 for holes. So adding up all together, we can list a table of a different scattering mechanism related with different phonons. So in total, there are 9 phonon branches in this material, because there are 3 atoms each unit cell, so 9 branches. Have different energy. They're all non-degenerate. This is a good feature for chiral phonons. Have different mirror symmetry. So particularly 4 of them breaks inversion of mirror symmetry. So they don't play a role in any scattering process. They have different pseudo-angular momentum. Okay, so they participate in 3 types of different scattering process. One is electron-electron scattering. So electrons jumping from one valence band to the other. And the whole scattering, and then indirect absorption, which means that the holes scatter with each other, and then light then there's additional photon that participate in the scatter. So seems that the time passes so fast. Sorry, let me go quickly. Then these rules are derived from symmetry only, but can also use first principle calculation to verify that indeed some scatterings are allowed, whereas some other scatterings are forbidden. So the process that we choose is to start with a polarized hole, which scatters to a phonon, and then we use the additional photon to pump energy such that the hole makes a inter-valley scattering and land to a different energy level. So the reason we choose 2 energy levels with quite different energy is because then we have to use a photon there, and this photon's polarization tell us if the electron-phonon interaction is chiral or not. So this is a 4-particle process, and then we can identify the phonon's angular momentum by the incident photon's angular momentum. So I will probably skip this, talking about how the many-body interaction matters in the line-matter interaction in this material. But basically, in this case, we'll just treat this whole as an entity, but its energy is affected by say the electrons simultaneously reside in the material. So using spectroscopy method, we can identify that once we inject holes, those holes have a certain energy that is basically a combination of one hole and two electrons in the connection band minimum. So this system is good because if you look at the spin, so this is spin triplet state. So once the hole and electrons stay there, they're dark. They don't have this optical transition, so they have enough lifetime for the phonons to scatter those holes. So this is our initial state. And then after injecting another photon, this hole jumps to the spin split off band in the other valley, which preserves the spin here. And then this hole can recombine with the electron and give some luminescence. By measuring the energy of the luminescence and the polarization of the luminescence, we can identify what is the final state of the holes. So this is a hole that is the result of a intervalley scattering with light. So I will skip that. And then question is, what type of photon is necessary to trigger that transition? And then it's easy. We can vary the infrared photon's energy, and then also the polarization. Then we identify that this transition can only happen with a threshold energy, and that corresponds to the minimum transition energy that is required to emit a photon. So adding the energy together, we know, here we go. Okay. So adding the energy together, we can identify what is the excessive energy released to the scatter phonon, and also adding the angular momentum together, we know how much angular momentum has been carried away by these phonons. So it seems that both these numbers agree with only one mode, that is so-called LO mode, with a certain energy that is within this error bar, and then it is indeed allowed for indirect optical absorption. So of course, this is a fairly complex scheme to verify chirality, but there are more advanced methods recently with the progress in materials growth. And this is actually Dr. Xiaodong Xu's work, so hopefully he will share more in next talk. So their group made very high quality materials such that the spectrum of these like electron hole recombination are very, very sharp, and the lifetime of this polarized holes are extremely long. So in those cases, then the phonons have enough time to be scattered scattered by this phonon, and then do an emission that is usually forbidden. So all these emission lines are forbidden, but then just only in high quality samples you can start to see something. And then they identified two possible mechanisms by which phonons can assist this forbidden transition. One is that the electrons do intervalley scattering and recombine, and the other is holes doing intervalley recombination, intervalley scattering and recombine. So in those cases, you have different selection rules, because electron-electron scattering only interacts with the TA and LO mode, whereas the hole-to-hole scattering only interacts with the LA mode. So indeed, they have identified 3 peaks that's related with the K phonons. And by looking at the polarization dependence, they can indeed identify where did the recombination happen, in K valley or minus K valley. And then those selection rules and the energy correspond very well with first principle calculations. So in general, these are the methods that use electron-phonon interaction and the excitonic recombination optically to probe the chirality of the phonons. I will skip that. Okay, so finally, I would like to discuss what does it mean by having chiral phonons, other than we can see chirality if there is any actual implications. So because chiral phonons carry angular momentum and there are certain selection rules related with it, it generally scatters less than typical phonons. So that the first thing, the consequence is that it has longer lifetime and potentially higher thermal conductivity. And such a protection does not require the phonons to be perfectly circular. And indeed, thermal conductivity involves a lot of phonons, right? As long as it's partially chiral, you will start to see effect. So here is an example of from first principle calculations. So you have the lines of atoms, and that propagates heat along these atomic chains. So the chain itself is refill symmetric, so it supports chiral phonons. And if this chain is by itself, then it's perfectly chiral. From first principle calculations, they showed that the chain itself, if it's a single chain, exhibit the highest thermal conductivity. And especially notably, that the main thermal conductivity is contributed by those places, those phonons with the best chirality. So either it's a gamma phonons, gamma acoustic phonons, so it's very low frequency, or the optical phonons also at the gamma point, which generally don't contribute to any thermal conductance because it's a strong scattering. But chiral phonons don't scatter. So in this perfect chains, the thermal conductivity is a few times higher than if the chains start to interact with each other in a bulk material, or worse, if these chains are coupled by some additional atoms. So that's about phonon itself. Also, the phonons can couple with both the orbital degree of freedom of electrons, or valleys, and the spin degree of freedoms. So the general Hamiltonian can be written in 2 terms. One, which is easy to understand, the phonons can scatter electron from one spin to the other spin, or one valley to the other valley. So this is basically the inverse process of the electron-phonon scattering probed in the optical spectroscopy before. But the other phenomenon is also very interesting, which is a dispersive coupling. So if there are chiral phonons inside the system, then this material is spin polarized. So this term exists basically because of spin-orbital coupling. You can have other basically dimensional analysis that to calculate what's the relationship between this lambda coupling and spin-orbital. But the result is usually on the order of say 1% to 10%. So what does this number mean? That means if you have 1 chiral phonon per unit cell, you're expect to generate about 0.01 H-bar of a magnetization per unit cell. And vice versa. If we have materials magnetize with 1 H-bar per unit cell, roughly, the phonons will change its energy by about 1% to 10%. So this is effective Zeeman splitting, right? So that means the chiral phonons actually have some finite magnetic moment. So these are some theoretical predictions saying that indeed this effect does exist in two-dimensional materials. Once you start to have a chiral phonons, then it creates some finite magnetic moment. And also the effect is this actually reversible effect or related effect has been experimentally and theoretically experimentally demonstrated in one way, that is, the phonons do split if there is a magnetic field, and then reversibly, if there are enough phonons, it will create a large effective magnetic field within the material. So these phenomena basically lead to an interesting question: why or how can we control these phonons, right? So theories are all good, right? So we know if there are a lot of phonons, then it has some effect. But so far, the optical process that we discussed rely on spontaneous electron-phonon coupling. So the phonons are random, and then the populations are low. So the big question within this field will be: is it possible to have a lot of chiral phonons that drives some effect, especially the spin dynamics? So there are a few ways to control chiral phonons coherently. One is by phonon anharmonicity. So basically means that if we squeeze a lattice to an anharmonic regime, it is then possible to create phonon modes that break time crystal symmetry. So this has been experimentally demonstrated where an effective circular polarized atomic rotation is generated by a very strong optical excitation within a limited time. So on the time scale about 100 femtosecond, the atoms basically draw a circle within the lattice. And then what people have observed is that this atomic circle actually start to excite magnons within the material. So now once this spin start to rotate alongside with the atoms, then those magnons are persistent. So even if the phonons are only polarized for a short period of time, the magnons will live there for much longer. So this is one way that that's the experiment. The other way also we have done experiment is just by direct terahertz field excitation. So suppose if we can have a terahertz field that rotates in as a function of time, then it can directly couple with infrareactive phonons. And indeed, we can probe the population of this coherent chiral phonons and distinguish it from the effective field. So the electric field also breaks time crystal symmetry, that's for sure. So that causes a big initial response of the material's magnetic and elastic properties. But then this field quickly goes away. It only lasts within 1 picosecond. But then the phonons there continues to rotate and then stays for a longer time. So I hope that with this actual coherent phonon populations, we can share with you more the details about how they interact with spin systems in the future. So to summary, the chiral phonons enable asymmetric scattering and chiral selection rules that breaks time crystal symmetry. So that causes the coherent chiral phonons to directly couple with excitons and spins, and potentially can lead to ultra-fast terahertz quantum operations. With that, thanks for your attention, and I look forward to questions.
Yeah, but very nice. Yeah, so this is quite a detailed description. Yeah, so maybe questions. Yeah. If I haven't seen any hand. Okay. Song. Yeah. Oh, you have a nice image, Song.
Hi. Okay. So this is Sang-Uk Chung at Rutgers University. Very nice talk. I have two questions. One somewhat specific. The other one more general question. First question is this pseudo-angular momentum. Does it have orientation? You have a K. K has certain orientation. So this pseudo-angular momentum has orientation. And related to the question is this magnetization you induce by chiral phonon. What is orientation of that magnetization? That's my first question.
Yes, thank you. So let's take a look at the direction here. It's all rotating along Z. So the pseudo-angular momentum is along Z direction.
I don't know what Z means. Z is a K direction?
It's the outer plane, yes, it's the outer plane. So this is two-dimensional plane and Z is outer
plane. Outer plane direction, even though phonon is moving in the plane?
So good point. So these plane waves are certainly, all the momentum are in plane.
Okay, I see.
But note that these are Brillouins on corners. So actually the phonon themselves don't move. So the group velocity is 0. It's just that the base velocity is in plane.
I see. So group velocity is 0. So it's kind of long wavelength limit. Okay, fine. So and then magnetization direction?
Yes.
Same.
Yes. So it will be along that direction. Yes, all of plane.
I see. Okay. Okay. So that I see. Let me see. Okay. Let me think a little bit. Okay, so that sounds okay, but this is okay. So basically, zone center. You said zone center or zone boundary.
So these are zone boundary.
Zone boundary.
Yeah, those are zone boundary. But
oh,
still,
that's zone boundary. Okay, so it's so it is a zone boundary. So it does have orientation. So that is in the plane.
Yes.
In the plane orientation, I mean, K direction is in the plane, right?
Yes.
K direction is in the plane. Okay. And I see. So let me think a little bit. So K direction is in the plane. And if you put mirror along the plane.
Yes.
If you put mirror along the plane, sample doesn't change any. K direction does not change any, and also magnetization direction does not change any. So that's good. Mm-hmm. But if you put mirror along, I think, so K has to be a particular direction. Okay, so then it's gonna work. Okay, so mirror symmetry, I think that's okay. So more general question is, so you define this chirality in terms of just broken space inversion and time reversal? That's enough for chirality in your definition?
Yes. So here.
Section is laughing because
no, I'm not laughing about you. I'm laughing about the Carol's. He's drinking wine while waiting to ask questions.
Okay. Oh, I see. Okay. Okay. Sorry, I was rushing to. Okay, I should be short.
Happy hour in Europe, man.
Okay.
So fundamentally, we define chiral phonons as something that does.
No, that's chirality. That's chirality.
Yes, chirality. Something that does not equal to its mirror image. So to fulfill these conditions, the system should have either broken inversion symmetry or time reversal symmetry. So this is just symmetry. Yes.
Well, okay. So you know, there is something called linear magnetoelectrics. Linear magnetoelectrics. They do have a broken space inversion and time reversal, but I don't think it does anything.
But they conserve PP.
Correct. So I think I think the definition, you know, this requires a long discussion. But only comment is that you think about so-called linear magnetoelectric, how that fits into your so-called chirality. Think about this. And one more question is, you know, so this also may be something you thought about, but there is something called dynamic magnetoelectric effect. Dynamic magnetoelectric effect. You know, people like Nicholas Baldwin has been discussing this. It seems like, you know, you call chiral phonon inducing magnetization. That looks very much like what she has been discussing, so-called dynamic magnetoelectric effect.
That's correct. Yes.
That is correct. Oh, I see. Okay, then everything is more clear to me. Okay. Good. Thank you.
Okay.
Thank you very much.
Yeah. Now your turn. Yeah.
Yeah,
go ahead. Yeah.
So Sango, yeah, very good segue into you. Yes, actually, this is correct, correlated to this question of the linear magnetoelectric effects on the PT antiferromagnets. I think he was referring to primarily the ones that Spalding and Fiebig had actually been studying optically in the insulators, right, in the oxides. And then we just have seen, for example, in manganese 2 gold, which is also a PT antiferromagnet, this a broken parity in momentum space that could possibly maybe couple later to, I don't know if it couples to phonons, but my question was to you a little bit. Now in antiferromagnets that we have some of these PT antiferromagnets that are chemically generous, but with spin-orbit coupling will break that chirality actually. We'll break that with the presence of the magnetic ordering and spin-orbit coupling breaks that mirror plane essentially. And you can, depending on the orientation of the Néel order, you can actually, these non-symmetric symmetries that open and close the nodal lines and the crossing points will have some implications. Have you looked, or has anybody looked at what those implications would be on this magnon, in this case phonon maybe, or electron-phonon coupling for this chiral phonons maybe in these systems?
I think those are very, very good questions. So far, for simplifying the physics, people are only, well, maybe it's a limited group of people, are still focusing on like high symmetry lines or high symmetry points. So for example, if we have a bulk material, then mostly we're looking along the axis with threefold symmetry. So those will be 1-on-1 for qubit structures. So in general, how does it fit to say linear magnetoelectric? So I have not think very deeply here. But I would say that on the phonon itself, I would see that with lattice actually breaking inversion symmetry, then it's easier to see the phonons have parallel.
Is the lattice itself does not? It's actually the presence of the magnetic order with the spin-orbit coupling that breaks it.
Yeah, that's right. So this is something more subtle. I believe, as you said, with spin-orbital coupling.
It's with the spin-orbit coupling. Without spin-orbit coupling, you will have the symmetry, but with the presence of spin-orbit coupling and the magnetic ordering, you will break that. Yeah.
Yes. So only when there's spin order, the inversion symmetry is broken. And in those cases, I do believe, just from symmetry argument, that it will have chirality, but how large it is, well, it really depends. So something I'm familiar with is the basically second harmonic generation from these systems. So they do have second harmonic, meaning that indeed they break inversion symmetry, but it's generally much weaker than if something that actually a lattice breaks the symmetry and the electron wave functions have broken symmetry.
Yeah, you need system with a strong coupling. Actually, we just in a metallic system, the equivalence that you see actually in -2 in this case is a very strong asymmetry on the band structure due to the ARPIS momentum flight of time of flight momentum ARPIS. You see this very strong
yes
symmetry.
So for system, for example, a ferromagnet with a very strong spin-orbital coupling. I mean, since spin waves are counterclockwise rotating in the order state, when you have a very strong spin-orbital coupling and also very strong spin lattice coupling. So which direction you'd expect I mean, compared with the paramagnetic state, which direction you'd expect the phonons to shift, the acoustic phonons to shift due to this chiral phonon.
So
what do you think? Yeah.
Yes. So the symmetry argument only applies to whether the interaction happens or not happens. So in terms of which mode couples to, say, the left circular or right circular mode couples to specific, say, ferromagnetic resonance, it depends. So these ultrasonic experiments has proved that at least indeed these ultrasonic attenuation in ferromagnetic materials are asymmetric. Yeah. So the question will be exactly is that left shear mode or right shear mode couples, and that actually depends on the actual lattice structure. Yeah, because those phonons unfortunately only carry pseudo-angular momentum. So look at those atoms, they are rotating, but you know it's not real angular momentum. It depends on which is the reference point. Whereas the angular momentum of the ferromagnetism is absolute.
I see. Okay, are there any other questions? Okay, yeah, very good. Yeah, if not, yeah, thanks, Hanyu, for a very nice talk. Yeah.
Thank you, very nice talk. Cheers.
Thank you very much. So
Yeah,
thank you for this new concept to me as well. So we hope that with our experimental technique, we can explore this PT anti-ferromagnetic systems.
Yeah. Thanks. Nice having you. Very interesting. Thank you.
Yeah, thank you.
Thank you. Have a nice day.